Hey everyone, welcome back to Bugnojutsu, the channel where we break down coding interview problems and LeetCode questions step by step, so you not only solve them but also understand the intuition behind every approach. In today's video, we'll be tackling LeetCode 1277, Count Square Submatrices with all ones, a very interesting dynamic programming problem that teaches us how to build solutions by reusing subproblems. If you've ever struggled with matrix DP problems, this is a must-watch till the end. The problem gives us a matrix made up of only zeros and ones. Our task is to count how many square submatrices exist where all the elements are 1. Now, when we say square submatrices, it doesn't mean only 2 by 2 or 3 by 3. Even a single one is considered a 1 by 1 square. We need to count all such squares of every possible size in the entire matrix and return that total number. So essentially, the matrix is like a grid of tiles, some being 1 and some being 0. We need to count how many all 1 squares we can form across the grid. Let's look at an example. Here's how the counting goes. Squares of size 1 by 1, every single one is a valid square. In this matrix, we have 10 of them. Squares of size 2 by 2. Now we look at groups of 4 ones forming a 2 by 2 square. We can find 4 such squares. Squares of size 3 by 3. Finally, there's one big 3 by 3 square in the bottom right corner. So in total, 10 plus 4 plus 1 is equal to 15 squares. That's the answer for this example. The trick to solving this problem efficiently is to realize that the size of the largest square ending at any cell depends on its neighbors. Here's the intuition. If a cell has value 0, it can't contribute to any square, so we just ignore it. If the cell has value 1, then it can form a square of size at least 1. But to see if it can be part of a bigger square, we check 3 directions. The cell above it, the cell to the left, and the top left diagonal. Why? Because for this cell to extend into a larger square, all 3 of those directions must also be capable of forming squares. So the size of the square ending at this cell is 1 plus minimum of top, left, diagonal squares. That gives us the largest possible square at that point. Then, if we add up these sizes across the entire matrix, we automatically count all smaller squares too. This recursive strategy with memoization ensures we don't repeat work. By caching results, every cell is solved once, and then reused multiple times whenever needed. Time complexity. We visit every cell in the matrix exactly once, and for each cell we do only O(1) work because results are cached. So the overall time complexity is O(m) times n, where m is rows and n is columns. Space complexity. We use caching for recursion, which in the worst case takes O(m) times n space. So space complexity is also O(m) times n. This problem is a classic example of how dynamic programming works in grids. Instead of brute forcing every possible square, which would be too slow, we reuse answers from smaller subproblems to build larger ones. Also, the same concept is very similar to longest square submatrix problems or finding maximal square of ones. Once you understand this recurrence, you'll be able to tackle those variations easily. Another key insight is, when you add up the largest square size at every cell, you're automatically counting not just that square, but all the smaller squares inside it too. That's the beauty of the recurrence. And that's how we solve count square submatrices with all ones efficiently using dynamic programming. If you found this breakdown helpful, make sure to like the video, subscribe to Bugnojutsu, and hit the notification bell so you don't miss any future problem explanations. Also, drop a comment below on what other problems you'd like me to cover next. Your suggestions really help shape this channel. Thanks for watching, and I'll see you in the next one.